In this video, you'll be able to understand the relationship between sending an voltage and receiving an voltage and a simple system link which is being connected to two generating station. How does or what all are the conditions for the flow of real and active power? So I'm Mohan BS, working as assistant professor in Department of EEE SJBIT. So this is a phase diagram, the circuit diagram of a simple transmission line of a single line. So taking the load and voltage as reference, showing here this as VL, and the current that is flowing in the circuit is assumed that the load is being inductive in nature and thus the current is there in fourth quadrant. If we had current as resistive, if the load is being resistive, considered as resistive, then this current would be actually in phase with the voltage. If this current or the load is being considered as capacitive in nature, then the current would be there in the first quadrant. So since the load is assumed as inductive load, as practically we have most of the load being inductive in nature, thus the current lacks the applied voltage or voltage drop across the load, and the current will be lagging with respect to some angle theta. And the same current is actually being supplied from the generator, and the same current is also being consumed by the transmission line as losses. So transmission line is made up of R and XL. The voltage of across R is given as I into R because the same current is traveling through the load and through the transmission line, and we are aware that voltage of across the resistance is in phase with its current. So I into R is the voltage of across resistance and that's in phase with the current. And we are actually in turn here to write the equation or the relationship between VG and VL. Thus adding on after VL will be at the end of the VL. So what we have got is voltage of across resistance and voltage of across the load. And the left out are VG and voltage of across inductance. And we are aware that the voltage of between I and VL or the voltage across V and IL would lag by 90 degrees. So if this is considered as x-axis, then the current is lagging by 90 degrees. Or with respect to this current I, voltage is leading for your inductive loads. Now here inductance is with respect to your transmission line. So if this is considered as x-axis and this is minus y-axis, thus the current is lagging with respect to the voltage across your inductance. As we are aware that we are intent to find the relationship between VG and VL, and here we are adding up the voltages, thus it comes after IR. So summation of VL, IR and IX, that is voltage up across inductance in your transmission line, will give us the generated voltage VG. And the angle between the voltage and current is lagging by some angle phi, and delta is the angle between your VG and VL, and this angle delta can be varied such that the angle is less than 90 degrees only your generated voltage can be produced. And in distribution system, this delta angle is slightly always lesser. Okay, so let us see what are these two, that is change in your VP and then change in VQ. There's real part, there is a real component of your voltage and real component is an imaginary component of your voltage or reactive component of your voltage. The voltage at the source are taken and the voltage at the source and load are related by. So as we apply KVL, we can write this equation, or with respect to this vector diagram also one can write the equation as VL plus I into R plus J XL. So we are aware the complex power is given as VLI as P minus JQ. This is your apparent power, and then your complex is given as V into I conjugate P plus JQ. So I is equal to P minus JQ into VL. So substituting the value of I in this equation, the equation reduces in this syntax. Now the next step is just trying to segregate the real part and the imaginary part. So as you can see here, VL RP by VL and x minus jx and minus jq by VL becomes again real component, as j into j, as we solve this becomes positive, and we write this component as your delta Vp and we write this imaginary component as your delta VQ. So I hope now you are aware what are these delta VP and delta VQ. So that is your active and reactive component of your voltage of your generator. So thus we can write VL as VL, VG as VL plus delta VP plus J delta VQ. If D is very small, if delta angle, this angle is very small in usually cases of a distribution as we told earlier, that goes to 0. Thus we can say VG is equal to VL plus delta VP. So solving it further, we get Vg minus Vl as Rp plus Xq by Vl. And what is this R? So this R is nothing but the resistance of your transmission line, and we assume that that is actually 0 and it's being more inductive in nature. Thus the equation further rises to Vg minus Vl is equal to Xq by Vl. Let us now consider a system linking two generation stations A and B as shown below. So we have this system which is linked, which is having a simple link between two generating stations. So initially the system is considered to be only reactive and R is being ignored. So here the system is considered only reactive system and not resistance. The machine at A is in phase advance of that at B, and V1 is greater than V2. That means we are saying that this machine angle voltage is being leading compared to V2 is what they're trying to say. Hence there is a flow of real and active power from A to B. So you can see the voltage difference is greater because the flow of real power and active power is from generation station A to generation station B. So based on that, let us write the vector diagram for representation. So V2 is taken as the reference again here. Current I is being lagging, and as we are aware the system is being inductive in nature. Thus with respect to the same current as it flows through, the voltage of across the system will be lagging. So thus if you take this as x-axis, this is your minus y-axis, right? And we are in turn to find the total voltage V1. So writing the voltage of across system at the end of V2, adding these two, that is V2 plus Ij of your system, gives us V1. And this is the angle between the generated voltage and at V2. And this current has two components. One is your imaginary component, other is your real component ID. So ID and hence P is determined by delta IQ, and hence Q is given by V1 minus V2. So by varying the generation excitation such that V2 is greater than V1, the direction of the reactive power is being reversed. But whereas now here what we have considered is, in this case V1 is greater than V2 and the reactive power is transferred and the active power is also transferred from A to B. So real power can be sent from B to A or A to B by suitably adjusting the amount of steam admitted to the turbine, and the reactive power can be sent in either direction by adjusting the voltage magnitudes. Now assume that the interconnected system as shown in figure B has some resistance and that V1 is constant. So that now we have delta Vp as Rp plus Xq by VL, or VL delta P is equal to Rp plus Xq, just cross multiplying this. And then we have here that Q is equal to V2 delta V minus Rp by X as we solve this equation, or we can simply say that this is equal to K minus Rp2 by X, where K is a constant and R is the resistance of the system. Thank you for watching the video. Please subscribe the channel to enhance your knowledge further.